Morning all. Last class we started our discussion about AC characteristics of op-amp. In that AC characteristics we are having two things. One is sleeve rate and the other one is frequency response of an op-amp. Already we discussed about sleeve rate. Now we are going to discuss about frequency response of an op-amp. So for the explanation of frequency response of an op-amp, we require Bode plot. Bode plot consists of two things. One is magnitude plot and the other one is phase angle plot. In the magnitude plot, we are going to show the variations in between magnitude and frequency, whereas in the phase angle plot we are going to show the variations in between phase angle and frequency. Now I am going to explain what is frequency response. Ideally an op-amp should have infinite bandwidth, but practically op-amps have decreases their gain when you are increasing the frequency. Ideally it should be infinity, but practically it is not possible. Why? Because when you are increasing the frequency, the gain is automatically decreases. The gain is depends upon the frequency because of the capacitive component present in the op-amps. That is the very important point. And this capacitive component doesn't show any variation when they are in the lower frequencies. But while you are going to increase the frequencies, then this capacitance show the decreased reactance. So the gain will be decreases at a rate of minus 20 dB per decade or plus 20 dB per decade, depending upon the polarity of the input voltages which we are applied at the op-amp. Such a gain reduction with respect to the frequency is called as gain roll-off. And the plot shows the variations in magnitude and phase angle of the gain due to the changes in the frequency is called as frequency response of an op-amp. And just now only I told you that the Bode plot consists of two things. One is magnitude plot and the other one is phase angle plot. When the gain in decibels and the phase angle is expressed in degrees, and we plotted the graph against the logarithmic scale of frequency, then we call that plot as Bode plot. Why we are going to be used logarithmic scales or logarithmic graphs for the Bode plots is we are going to increase the frequency ranges to gigahertz as well as terahertz range of frequencies. In those cases, it is not possible to represent those frequencies in the normal graph. That's why we are going to use the logarithmic graphs. And next, obtaining the frequency response. Why I am telling that frequency response is the gain is not infinity when the frequency will be increases. Whenever you are increasing the frequencies, automatically after reaching a particular frequency, maximum frequency, then gain starts reduced. Okay, so why the gain is reduced? Because of frequency is capacitive component present in the op-amps, and this capacitive reactance doesn't shows its effect when the frequency is low. Whereas in case of when frequency is increases, then it shows the reduced reactance. So the op-amps are designed with the help of BJTs as well as FETs, and the BJTs and FETs are having the junction capacitance. Obviously, if you are not representing any capacitive component in the equivalent circuit diagram, but because of the construction of the op-amp with the help of BJTs and FETs, and it consists of junction capacitors. and here I am going to explain the gain reduction at a higher frequency. So I am going to include a capacitive component in the equivalent circuit diagram of an op-amp. So I will get A0 is equal to A0 L divided by 1 plus J into 2 pi F into R0 into C. Okay, that is the transfer function, and the op-amp is having the break frequency, and the op-amp is having higher frequencies. And now see, if I am assuming F0 is equal to 1 by 2 pi into R0 into C, then obviously A0 L of F is equal to A0 L divided by 1 plus J into F by F0, where F0 is called as break frequency. Until that break frequency, there will be no change in the gain from the zero hertz frequency to that frequency, break frequency. The gain is constant. So after that break frequency, the gain decreases at a rate of, that may be 20 dB per decade or that may be 40 dB per decade, that depending upon the transfer function. But in this case, here the gain will be decreases by minus 20 dB per decade. So F0, 0 to F0 is nothing but the bandwidth of an op-amp. For an ideal op-amp, the bandwidth will be infinity. Why? Because the gain will be infinity for all the ranges of frequency. But whereas in case of practical op-amps, the gain is not infinity. Until the cutoff frequency, the gain is constant. After that, the gain will be decreases. And next, here I am representing the transfer function in terms of magnitude as well as phase angle. Whenever we are representing in terms of magnitude, we have to consider modulus of gain. So modulus of A0 L of F is equal to A0 L divided by square root of x plus ij, means square root of x square plus y square. Here we are having 1 plus j into f by f0. So we will get square root of 1 plus f by f0 whole square. And the phase angle will be represented as minus of tan inverse of imaginary part by real part. And if we are having the pole, then we will get tan inverse of, then plus tan inverse of. But here we are having the roots are 0, so we are having the 0, then we are having tan inverse of real part by imaginary part minus tan inverse of imaginary part by real part. Why? Because if we are having 0 and pole. But in this transfer function we are having only pole, so we are getting tan inverse of f by f0. So here for the frequency response, you have to remember two important things. One is gain crossover frequency and the other one is phase crossover frequency. What is gain crossover frequency? The frequency at which the gain of an op-amp will be equal to 1, which is expressed as 20 log of 1 is equal to 0 dB. That particular frequency, that means the gain in decibels is equal to 0. That particular frequency is called as gain crossover frequency. Whereas coming to the phase crossover frequency, the frequency at which the phase angle crosses minus 180 degrees, then we will be treated, that frequency is called as phase crossover frequency. For the stability of an op-amp, we have to follow the Brackhausen criteria. It has two rules. One is the magnitude of the transfer function will be equal to 1 and the phase angle should be less than, and the phase angle should not cross minus 180 degrees. Then we will treat that system as a stable system. For this, we have to consider gain margin as well as phase margin. Gain margin is calculated at phase crossover frequency, whereas phase margin is calculated at gain crossover frequency. And gain margin is equal to minus 20 log of modulus of A0 L of F, whereas phase angle is 180 degrees plus angle of A naught L of F. If both the values are positive, then we can tell that the system is stable. If any one is negative, then the system will be unstable. If both are satisfies their equation, that means the gain is 0 dB as well as phase angle touches minus 180 degrees, then we will treat that as a marginally stable system. Why I am calling it as marginal stable system is once we crosses that frequencies, obviously the system will be oscillates. That means the system will be unstable system. And here I have shown you the board of plot. That is, in that I have shown you the magnitude plot as well as a phase angle plot. Here we are having only one break frequency. So the maximum phase angle should be minus 90 degrees only. So it should not cross minus 180 degrees. So if the system consists of single break frequency, then must and should the system will be a stable system. If the system should consist of more than one corner frequencies, that means if the system will consist of 3 break frequencies, then the system is obviously unstable system. So if you want to bring the unstable system into a stable system, then you have to use the frequency compensation technique, whether it may be the external frequency technique or whether it may be the internal frequency technique. You have to bring back that unstable system into a stable system. Here I told you that the crossover frequencies as well as gain crossover frequencies as well as phase crossover frequencies, and also I explained the bandwidth. Okay, now these are all the things which we will know from the phase angle plot. As for an op-amp with a single break frequency, so unity gain single break frequency after F0, the gain bandwidth product is constant and is equal to unity gain bandwidth. If op-amp consists of single break frequency, then we will be treated it as unity gain bandwidth. So UGB is equal to product of gain and bandwidth. So A naught L into F naught. So similarly, if the closed loop op-amp will consist of a single break frequency, that is also called as unity gain bandwidth. There also you can treat it as UGB is equal to AL into FF. In the problems, sometimes they will not give the break frequency or corner frequency. Simply they will give unity gain bandwidth or open loop gain of op-amp. From that we can easily calculate the single break frequencies. Next, with this graph we have drawn those magnitude plot as well as phase angle plots. Now coming to the modes of operation, the modes which we are going to be used for op-amp. Mainly we are using 2 modes. One is closed loop op-amp and the other one is open loop op-amp. For the closed loop op-amps there will be no feedback, whereas for the open loop op-amps there will be no feedback, whereas coming to the closed loop op-amps there will be a feedback from the output to the input, and that feedback may be a negative feedback or it may be a positive feedback. If the feedback will be applied at the inverting terminal, that means the output voltage is 180 degrees phase shift with the input signal, then we will be treated it as negative feedback. And if the output voltage is in phase with the input signal, then you will be treated it as positive feedback. And listen carefully whether the op-amp is operated in the open loop or whether the op-amp is operated in the closed loop. The output voltage of the op-amp is always depends upon input voltage, but the output variation is always depends upon the input voltage. But in the closed loop op-amps, the gain will be in the open loop op-amps, the gain will be very high. So even for the small amount of the input applied at the input terminals, because of the noise and because of high gain, those noise input voltages are also amplified and generated the output as saturation voltages. That's why we will not be considered the op-amp in the open loop configurations. And whereas coming to the closed loop operations, always the output is part of the output is fed back to the input. Okay, so in this case the gain is not infinity. The gain is reduces when compared with the open loop op-amp, and the configuration in which output depends on input but output has no effect on the input is called as open loop op-amp. That's what I want to tell now. Okay, that's I want to tell you. The output voltage has no effect on the input, then we will be treated it as open loop. And if the output is showing some effect on the input, then we will be treated it as closed loop op-amp. Here I am showing you the configurations of op-amp in the open loop. And no feedback from the output to the input used in open loop configuration, and the op-amp is having a high gain, as well as op-amp can be used in the open loop configuration in three ways. One is difference amplifier, and the other one is non-inverting amplifier, and the third one is inverting amplifier. What is difference amplifier? In this difference amplifier, the output voltage is directly proportional to the difference between two input signals, which is nothing but the differential amplifier. So to remove that proportionality constant, we are placing a constant of proportionality. So here we are taking it as AOL. Why? Because here we are using it as an open loop configuration. So V0 is equal to A0L into VD. Okay. Now coming to the inverting amplifier. How can we conclude this as an inverting amplifier is when the input is applied at any one of the input terminal, if you get the output as 180 degrees phase shift with this input signal, then we will conclude that the input is applied at the inverting terminal of an op-amp. So V0 is equal to A0L into V1 minus V2. Now in this case, generally while we are considering the VD value, always non-inverting terminal input minus inverting terminal input. So here V1 will be 0, and we are applying the inverting op-amp means we are applying the input at the inverting terminal V1. V2 is equal to V1. So V0 is equal to minus A0L into V1. Here I am treating it as V into, but when we are treating only one input, then we will be obviously taken as V in 1. Okay, so if you clearly you can clearly identify V0 is equal to minus of A0L into V in 1. So obviously there will be a 180 degrees phase shift between the input and output. That negative symbol will be representing. And coming to the non-inverting terminal, if the input is applied at any one of the input terminal, if you are getting the output as in phase with the input signal, then we will be treated it as the input is applied at the non-inverting terminal. So A0L into non-inverting terminal minus inverting terminal voltage. So A0L into here, now we are applying the input at the non-inverting terminal. Obviously we will be connect the inverting terminal to ground. So we will get V0 is equal to A0L into Vin. Here we are not getting any negative symbol. So we can treat that both the input and outputs are in phase. And next, general features of IC741 op-amp. IC741 has a high performance monolithic op-amp IC. It is available in 8 pin, 10 pin or 14 pin, and it can be operated over a temperature range of minus 55 degrees centigrade to plus 125 degrees centigrade. Even in our labs also, that means in our engineering labs also, we are going to be using this IC741 op-amp. The features of IC741 op-amp is it doesn't require any external compensation technique. Okay, it has internal compensation technique. Okay, and the next one is short circuit protection provided, and offset voltage, null capability, and large common mode and differential mode range. and no latches up are using in this IC 741 op-amp. Not only these things, you can also write the features of differential amplifier also. Why? Because for the construction of any op-amp, at the input stage we are going to be used differential amplifier. So features of the differential amplifier, along with you can write these also. So until this